Hello, welcome again to the lecture series on vehicle dynamics. So we'll continue our lecture on handling. In this part we will discuss testing of handling. Here how to test, for what to test under steady state conditions is what we are going to discuss about. So first we'll talk about three types of test. One is the constant radius test, constant forward speed test, constant steer angle test. Probably in the beginning of this chapter, in the first video, I just spoke about these points. Steady state response to steering inputs, taking steering angle as the input, yaw velocity as output, lateral acceleration as output, radius of curvature. That's what we will test now. Okay. So, constant radius test. In this constant radius test, we'll consider a circle of constant radius r. Correct? We make the vehicle go around this. Then we will measure steer angle, okay, forward speed. So those kind of parameters, right? Or we will write during the test the steer angle delta, forward speed, yaw velocity, or lateral acceleration of the vehicle we will measure. I think yaw velocity, lateral acceleration ay, right? Because here delta is equal to 57.3 L by R into K V squared by R. Correct now? R velocity. If you know other things we can find out. This is nothing but again lateral acceleration. Yes. Yaw velocity we can measure using a rate gyro. If not, lateral acceleration or forward speed, right? That we can do it. Lateral acceleration can be measured by an accelerometer or from the other equation yaw velocity into forward speed. Correct? Not V by R. I think I have defined here yaw velocity. Correct now? What is the definition of yaw velocity? R is equal to V by L. Sorry, V by R. R is equal to 57.3 V by R. Correct. Right. .3 V by R. Correct. Based on the relationship between the steer angle and lateral acceleration or yaw velocity obtained, handling characteristic can be evaluated. Basically, I will explain how to conduct these three tests. Find the handling characteristic. That's a simple thing. Now, constant radius test. So now you go to proving ground, select constant radius track R. That is done. Drive the vehicle at a speed of 10 kmph. Note down the value of delta. R is constant anyway. So now delta value is known. Vehicle speed is known. R is known. Calculate the lateral acceleration. So delta and lateral acceleration. Get that point. This is initially 57.3 L by R. Okay. Next, change the speed to 20 kilometers per hour. Again, go around, note the delta. So again, you will get this point. 30 kilometers per hour, same way you conduct the test. You'll get number of points. Okay, join them by a curve. Here you are getting positive gradient. So your understeer gradient is positive. So it is understeer. Here it is negative. It is oversteer case. So there's a point at which positive to negative 0 gradient, that is R equal to, right. That's where it changes from understeer to oversteer. It's a neutral steer condition. Not neutral steer condition, it changes over. That's all the point, right? This is neutral steer condition. Or this point, right? Okay. That's how you can do the constant radius test. Once you have this curve, probably you can find what is the maximum lateral acceleration we can have. Maximum lateral acceleration we can have, so that it still remains something like understeer, or what point it will become oversteer. Okay, so this is one thing. For that vehicle we can find out. Same a constant speed test. Now what you do? Take one circle, next another circle, next another circle, like this. R is changing. Okay, R is changing. Velocity is constant. So delta will also change. So velocity you can choose maybe 30 kilometers or 40, 50 kilometers. Okay. V is known. RG is known. And steer angle is known. Mark this point. Change R value. Again you will get another point. Join all of them. You will get the handling characteristic. So this region, it is a positive gradient. So it is understeer. Here it is 0. Then after that it becomes negative gradient. This oversteer condition. Okay. Constant steer angle test. Now we have to change the velocity. Also we have to change the R value, so that the delta should remain same. Okay. So here the vehicle is driven with a fixed steering angle at various forward speeds. Curvature versus lateral acceleration curve is drawn and the handling characteristic is determined. curvature is 1 by r. Or you can say here omega z by v, right? And this is lateral acceleration. Okay, from here again, this one is understeer. If you go this way, yes, going like this is a negative, going this way it's positive, right? We can find from this. Okay, these are the three tests, handling characteristics. From that, you will come to know the understeer gradient of the vehicle, right? I think the best one is this test. Correct? I think the constant radius test is the simplest and requires little instrumentation. Constant speed test is more representative of the actual road behavior of a vehicle than the constant radius test, as the driver usually maintains more or less constant speed in a turn and turns the steering wheel by the required amount to negotiate the curve. The constant steer angle test is easy to execute. Okay, fine. Transient response. Now we were talking about steady state handling. What is transient handling? So to attain a constant speed of, let us say, 50 kilometers per hour, we start at zero speed. 0 to 50, this is what you call it as your transient condition. After that, I maintain constant speed or constant radius, that's fine. But here to here, vehicle will be in a transient state between the application of steering input and attainment of steady state motion. The behavior of the vehicle in this period is usually referred to as transient response characteristics. So, something like this. Assume that I am driving the vehicle, then I am entering into a corner. So, I'll be coming with a speed of something like 100 kilometers per hour. By the time I enter here, I may come down to something like 60 kilometers per hour. Correct? So, in this region. After that, I'll maintain constant 60 kilometers per hour and radius is also constant. That is steady state. But in this region, okay, I was at high speed, I lowered down. That is what the transient business is. Correct? And I'll give a steering input also here. Correct? Vehicle will be in a transient state between the application of steering input here and the attainment of steady state motion. Okay, fine. The behavior of the vehicle in this period is usually referred as transient response characteristic. The overall handling quality of a vehicle depends to a great extent on its transient behavior. The optimum transient response of a vehicle is that which has the fastest response with a minimum of oscillation in the process of approaching the steady state motion. Now I need to model the vehicle. Okay, means I must consider that inertia effects, acceleration and deacceleration effect, and I need to model this vehicle. Vehicle is moving in the forward direction, that is one thing. So one equation for that degree of freedom. Also the vehicle is taking a turn about z-axis, it is going to rotate. So there should be another equation for that degree of freedom. Okay, this is the vehicle taking turn, that's fine. So I is inertia and omega is the angular velocity, rotation. And the forward speed v, again it can be in the x direction. I should do it vx vy. Okay, these are the coordinates at that point. Then we can resolve about this coordinate system. So vx vi. Then fine, it move from here to here. Again, this velocity would have been Vy, dVy and Vx, dVx. So it's increase in velocity and angular this thing, right? So considering these two conditions, I should write two differential equations, one considering linear motion, another considering rotational motion. Then I reduce this state equation into state equations, the differential equation. Okay. Then I'll be getting this kind of equation. This is of the form Ax plus Bu is equal to C, kind of an equation. We'll get this. This is A, this is X, this is matrix B and matrix input. Okay, right, C. So we are going to get, you see here, these are acceleration terms. This is the linear acceleration. You can say double dot kind of a thing. This is angular acceleration. Linear velocity, angular velocity is equal to some constant values. So now the question is, these differential equations, I have to solve this differential equation. There are so many ways I can convert them into state equations and I can solve them. Great. So I can use MATLAB or whatever it is, I can solve this equation. Then I can study how exactly the vehicle behaves if I have given a step input. That means step steering or ramp steering, how exactly the vehicle behaves, I can find out. Okay, so this I can simulate on Adams also, right? Step steer, ramp steer or sinusoidal input like this. So if you know the software, we can do this. You can just open up, go to the car module and we can do this transient behavior response. You can use Simulink also. So it's various ways we can do it. So here the vehicle step steer is given. This is what is happening here. You see. In fact, the vehicle is sliding and going. That is a pain problem. It's going out of control. Right. And now, similarly, I can simulate ramp steer and all those kind of a thing. Then if it is something is going wrong, we can find out what parameters has to be manipulated in this equation so that it will follow the contour or attain the steady state. Correct? That's very important. We can do that. You see here. Suppose in this case, this is the kind of input I have given. This is the output. So it is going to meet that requirement. Something going out of this output is more than the input, then it is going out of our control. Right. It is possible to simulate this and learn these things. I have not solved any problem here as such. Directly I have full vehicle. On the Adams, I have just done one or two examples. And I have not even changed the parameters to see that I have just arbitrarily given some values and I wanted to demonstrate you can simulate like this on the Adams. And I have not tried to simulate this to see that it is always stable, right? Okay. Fine, you can do this. That's not a problem. So many vehicle dynamic tests on the proving ground we do. So when you go to any car manufacturing company, they will have a proving ground to test all these things. So the intent of this test procedure is to subjectively determine the road holding ability and handling characteristic of a vehicle. We can do high speed oval test, circular skid test, braking test, durability test, slalom test, elk test, U-turn test, okay, handling circuit and so many things like this. Okay, so you will have a proving ground something like this. Okay, so that you should be able to conduct all possible tests. So you can simply high speed, you can call it as a oval test. The video which in the beginning of this topic, if you run that video, you will come to know how these tests are conducted, right? So this is the high speed oval test. Here you have a U-turn test. Here L test. See here, one lane, go to other lane, come back to the same lane, right? Okay, then you can do circular tests, right? Then slalom test, you can do like this. Okay, the football player practices the same way. You can do the slalom test. Okay, you can do endurance test by running your vehicle in all these kind of rough roads. Okay, so many other tests they do it. Okay, on this proving ground. Of course, inside the laboratory also we can do this. This is while building each system we can do this. Set right, but finally we have to go to the proving ground and test them. Normally high-speed oval test is done to test the wheel motion and we can record the data, analyze the data, and any setting has to be done, we can do that in wheel motion test. Okay, we can look at the camber, the caster, these kind of things like that. EL test, it is double lane change. You're going like this, change the lane, again come back, double lane change. Okay, vehicle handling during fast lane change. U-turn, you can study body roll, roll steer, and lateral compliance. Circular skid test to test understeer or oversteer vehicle, we can do that, which I explained earlier. Slalom test, vehicle dynamic analysis, wheel packaging calculation like camber change and all these things. We can do this. Okay, now the question is how to do this test. I think that testing agencies or test centers, they will give you the standard manuals. So as per these manuals, we have to conduct this test. In India, we go to Automotive Research Association of India. So they will provide us all those standards. Using those standards, we test this. Correct. And after the testing, they should certify. Okay, this is just vehicle dynamics. There are many other tests which I'm not talking about now. So this association, they will do all the tests and finally they certify the vehicle. If the vehicle is not passing any test, I think you have to take the vehicle back and redo that. Maybe in the design changes or manufacturing changes, whatever it is. Okay, these are the procedures. So while testing you can do. This video is not working actually, vehicle dynamic test. I will just see, click on that. Okay, you probably, if you can catch hold of this video, Krypton, you see that on the internet, you should be able to run this. They will explain all the tests that vehicle dynamics test that we conduct on a proving ground. Okay, right, sir. And another thing is something like rollover. This I explained earlier. Rollover limit, static stability factor, all these things I have explained earlier. Correct. If this is the vehicle, I think when I was explaining about lateral load transfer, I explained this. Correct. So suppose This is W. I think I'm going like this. Let us say, let me put this as W left, WR. So WL is equal to, I said, weight and this length. Let us say LR divided by track width. So I'm taking the turn like this, means this becomes inner, this becomes outer. So lateral load will increase. That load I said W by G AY, W AY by G H by T. Mila. So I think WL is going to be WLR by T plus W AY by G H by T. Other one is W right is equal to W LL by T minus W AY by G H by T. Now there is negative sign, here there is positive sign. If I go on increasing the lateral acceleration, this rod will lose the weight, this wheel will lose the weight, and this will start gaining the weight. And a point will reach, if I go on increasing, this will become 0. That time, this gets lifted up and this turns over. That is rollover. So that I have proved it is equal to AY by G is equal to H by 2T. So that is rollover. So you can use fish hook test. National Highway, what is this American organization? National Highway Traffic Safety Administration. National Highway Traffic Safety Administration. Their specification, fish hook test. Okay. So now you see here how exactly you have to steer. All these things have been specified. One is for the right turn, another one is for the left turn. Okay. Now, okay, we have studied, like, we'll talk about now another very important control that we use in cars. That is what you call it as your electronic stability program. You call it as ESP. We have studied about mu circle earlier. It drew a circle like this. This I called it as linear acceleration. This I called it as lateral acceleration. I called this as GG diagram, or I called this circle as mu circle, like this. So on a good road, maximum acceleration possible is mu g, I said. That is the maximum limit, even that is not possible. Maximum deceleration is also, I said, mu g. Maximum lateral accelerations possible is also equal to mu L. We say mu L is equal to mu, say, mu g. Correct. Now, suppose if you take highlighter, ink color. Right. Suppose if you exceed this acceleration, your vehicle is going to spin. If you do this way, the vehicle will skid. Okay, the vehicle will be skidding. Here, if you exceed this, the vehicle will skid. Wheels get locked and then skid. Here, vehicle will spin. If you exceed this, vehicle will slide. Okay, these things we have started. So here, what you can call it as, this is something like yaw effect happens. Okay. So now, how do we control this? By chance, a driver exceeds this point, to avoid this, we said TCS, traction control system. To overcome this situation, we have explained ABS can be used. To overcome this situation, we are talking about yaw control, that is what electronics stability program is. Okay, ESP. So they call it electronic stability control, electronic stability program, and so many names. I think these are all the various manufacturers, they call it with different names. As I said, this will have ABS, prevents wheel lock under braking, so skidding can be avoided. TCS prevents wheel slip during acceleration, that is fine. And side slip control, that is stabilizing. Okay, cornering, stabilizing cornering, yaw effect, we can reduce yaw control, you can do this. Okay, now for example, what it does, there will be a lateral G measuring sensor. So you will have an accelerometer which will measure lateral acceleration. This will measure the vehicle speed, capital V. This will measure AY. This will measure delta. Okay. So what is the maximum lateral acceleration, maximum vehicle speed, all this kind of thing is fed here. All these sensors will feed the actual values. What is the maximum, right? Or what is the real yaw rate, you can compute. So which direction it is yawing, all these things you can compute over here. Okay, so we have studied what is yaw rate, that is V by R. So you know, otherwise you know it is yaw gain, yaw rate gain, that equation also we have developed. So what is happening to the yaw rate gain, whether from that it will decide whether the vehicle is oversteering or understeering, and based on that decision is taken. So here, this is the vehicle. Look at these things. It is supposed to follow this path, correct? this vehicle will go here, then it is following this path, it is trying to oversteer. How do we avoid oversteer? Then once it is sensed, you see here, the signal is sent to this brake and brake force is applied here. This brake force and center of gravity is here. This radius will create a clockwise momentum. This fellow is trying to rotate like this. So, and make the vehicle follow the path. Is that okay? But continuously the sensors will be measuring the position. Continuously yaw rate will be calculated. And the system will be in a dynamic state. Continuously it will be measuring and making the corrections. Look at this. This is what is really happens. Suppose you are traveling like this. This happens when you are traveling on a highway. All of a sudden somebody enters like this. So to avoid this, we are trying to take a turn like this. So this is already V is very high, R is short, and lateral acceleration is very high. Chances of vehicle oversteering is there. In that case, this comes into picture. So that's what exactly it does. It stabilizes the vehicle and see that it follows the path. So that's how it controls. Is basically it will apply the right amount of force to the right wheel and create a counterclockwise moment and stabilizes the vehicle and reduces the yaw rate. It is oversteering. Understeering, you can see here. This vehicle is supposed to follow this path. Correct? The vehicle is going in this way. So it's understeering. I need to steer here back to this point. So what needs to be done? See that. Here if I apply a brake force, this force and this point will create one moment like this. And this force, because lateral force will act like this, this force about this point will create another moment like this. So see that the vehicle is on the path. That is what is happening. If required, appropriate engine control calculations will also be done, right? The algorithm will take care of these things. You see here, another is standing start slip control. When you start, all of a sudden, if one of the wheel is on the wet surface, then what is happening? It will apply brake on that. Correct. More. See that. It will see to it more traction is applied on this. See that it takes a turn like this, so that it will take a smooth turn this way. Right? You can see that it follows this path. This force about this point, so here it will create a moment like this. Right? So same thing under cornering. Okay, you can see here it is trying to understeer too much, right? Sorry, yeah, oversteer too much. Then you can apply the force, and around this point you can create this moment, and you can see that the vehicle follows the path. Correct? No? Right. So basically, then what is this electronic stability program? As you have your sensors. Basically, we have to maintain measure lateral acceleration, and also you have to measure the vehicle speed. Okay, you have sensors, that is yaw rate sensor with lateral acceleration sensor. Okay, then you have steering wheel angle. Okay, when you are steering, you are measuring, say, delta. Here this is a rotational part of it, so you can also use a gyro, right? So gyro is there, lateral sensor is there, right? Then a steering wheel angle sensor, that is delta. Then primary pressure sensor, here you have, right? Then wheel speed sensor, which will measure omega. Okay, all these inputs are given to this. Then you have the ESP controller. Then here you have, okay, this is engine part of it, like slip controller, EDDC, engine drag torque controller, like. Okay, then you want to apply the brake and all that. Suppose you are interested in controlling which way want to brake and all that thing, and based on our whatever algorithm you have put in over here, based on the algorithm, then that particular actuator is actuated and the brake is applied. Okay, definitely developing after understanding this theory, it is not very difficult to develop the algorithm over here. Okay, so we can do that. That is not at all a difficulty at all. Earlier I have told you how to develop TCS algorithm, similarly ABS algorithm. Now the equations, looking at the yaw rates and all that thing. So whether the yaw is gaining positive or negative, from which wheel it is happening, based on that we need to do this. Okay, apply the brake. That's the kind of it. In the meantime, it is necessary to control probably engine speed. Correct. Then definitely we can do, like, throttle control, reduce the fuel flow rate. Correct. Amount of fuel to be injected, that you can control. That is actually a fuel, automatically it gets controlled over there. So that way we can manage the speed also. That's how we can use this ESP controller. So there are many videos available from Bosch describing the ESP working. You can watch this.